energy storage potential, together with an estimation of the implications in the penetration of renewables and the operational mode of the conventional units. Now, from the preliminary study presented yesterday, the main outcome is that pumped hydro storage systems is a suitable storage technology to achieve high RES penetration in the power system of Cyprus, avoiding unnecessary RES energy curtailments. Pumped hydro is a mature and technologically advanced energy storage technology, whereas the existing water reservoirs in Cyprus provide an important potential for energy storage application at relatively reduced cost, providing many side benefits. The main objectives of the specific part of SREC project were sizing and siting of storage and hybrid plants in Cyprus, in the framework of which a map-based database was prepared, including all the main technical parameters and of the proposed plan. Additional objectives were the estimation of possible implications of the operation of hybrid plants, together with smart operation algorithms for the whole Cyprus transmission grid and the simulation of the grid's behavior in order to quantify the impact of various storage and RES scenarios. For appropriate sizing and siting selection, the constraints presented at the specific slide have been taken into account. The table on the left shows a TRL ranking and typical main characteristics such as energy capacity, round-trip efficiency, and response time for different energy storage technologies. And the table on the right shows the services that they provide, together with the major technical issues experienced so far. All of these data recovered are available and according to the European Association for Storage of Energy. Now, continuing with assessing the underlying potential of storage in Cyprus, additional common constraints should be taken into account, such as to find suitable landscape and available land for the potential required project's capacity with no significant environmental or grid connection issues. For the same point of view of constraints, the potential sites considered have to have at least one storage reservoir that is not currently used for potable water, and significant height difference for the siting of the second water state storage reservoir. The preliminary investigation of the potential size and siting of pumped hydro storage projects in Cyprus resulted in the specific map-based database presented here. What is included in this map is the siting of the upper and lower reservoirs for each potential pumped hydro storage plant, together with some information on the required reservoir volume that has to be created. The analysis here is not so high probably, but this map is available through our project partners in any other case. Now, further investigation provided data on long-term water availability of the reservoirs and their filling percentage, also in drought periods. The pumped hydro storage systems were sized based on worst-case scenario of water availability, and this fact probably answers the question asked from the panel yesterday, taking also into account the other crucial design parameters and assumptions following specific steps during calculations. For example, the required volume of the upper reservoir together with the available height difference between reservoirs and the length of the penstock led vice versa to the calculation of the nominal power in megawatts, the nominal water flow, and the suitable penstock diameter. As an assumption, the nominal autonomy of the system was calculated for 70% use of the upper reservoir water content. Estimation of the cost of the proposed system was also performed based on the sizing and dimensioning, and of course, recalculation of the crucial parameters, such as the upper reservoir volume and the potential nominal power, was also took place, so that the nominal autonomy will be at least 10 hours. The resulting pumped hydro storage systems were ranked by employing different selection and ranking criteria through a multi-criteria decision-making analysis. These criteria are mentioned on the first column of this table here, indicating, for example, whether or not the lower reservoir's water content is above or below 40% of its nominal capacity, whether or not the project's capacity is above or below 10 megawatts, whether or not the autonomy exceeds 10 hours, if there are any environmental or grid connection issues, if there is a need for a southern main water pipeline, and if the land of the upper reservoir is private or not. The contribution, or in other words, the weight factor of each criterion to the final ranking score for every pumped hydro storage system is represented in columns named rank 1 and rank 2. And the range of the final ranking score extends from 0 to 9. So, based on this multi-criteria decision-making analysis, the potential pumped hydro storage systems were further ranked as first and second priority. The table on the left concentrates design parameters emerged from sizing and dimensioning of the investigated pumped hydro storage projects, while the table on the right, more specifically within the last column, the ranking results for the same projects have been highlighted relatively and depending on the final score. So, first rank projects have been identified with a total of 275 megawatts of nominal power, having a rank over 6 and water content of lower reservoir greater than 40% of its capacity. The other projects of ranks equal to or less than 6 account for another 229 megawatts nominal power. Important to mention here that the nominal power of the pumped hydro storage systems may be increased by increasing each project's relative parameters for that purpose, such as the upper reservoir and the penstock, resulting in this way to increase capital and operational expenditures. Now, regarding the estimation of the impact and implications of the potential storage projects, the dispatched model was used. And for the specific investigation, it has been assumed that by 2030, RES penetration will be maximized as more PVs will be installed and the Cyprus grid will remain isolated. Moreover, up to 725 megawatts of pumped hydro storage systems may be installed, having nominal capacity for 8 hours, and the total annual demand for 2030 will be approximately 6,000 gigawatt hours. The installed capacity distribution for the cluster generators that has envisaged is presented at the table here and was integrated to dispatched models as a main input parameter. Continuing with the results from the model simulations, table on the left of the specific slide concentrates output parameters such as total energy production, unserved load, RES penetration achieved, and curtailed energy merged, system cost, and unit energy cost in terms of euros per megawatt hour produced. For an installed hybrid storage capacity range from 0 to 725 megawatts. Zero installed capacity means that no pumped hydro storage system is installed. On the right side, there is also a graphical representation of the most crucial parameters with a hybrid storage installed capacity on the horizontal axis. So, in case of maximizing RES penetration by 2030 and without installing any energy storage technology, there will be unserved load, as it seems here, even in the optimal scheduling configuration. RES penetration in blue color on the graph increases from 30% in the case of no storage facilities to 45%. For pumped hydro storage system capacity of over 500 megawatts, the RES penetration increases only for 0.5% for over 200 megawatt additional pumped hydro storage system. System cost, red colored on the graph, and unit energy cost with green are only marginally decreasing for pumped hydro storage systems of over 500 megawatts installed capacity. Finally, the curtailed power in purple, here in the graph, decreases by by 60% only by the first 275 megawatts of pumped hydro storage capacity, when at the same time their risk penetration potential increases by 10%. For further investigation of the impact of the storage systems, more scenarios of energy storage capacity from 4 hours to 15 hours were examined for the 275 and the 500 megawatt pumped hydro storage systems, and the respective results have been concentrated again in a similar table here. The main conclusions that came out are that the storage capacity of 8 hours is considered to be optimal for both of the systems examined when compared to 4, 12, and 15 hours, and in terms of the risk penetration increase. Moreover, the system cost change from 8 to 12 hours is marginally decreased, while unit energy cost is decreased by 0.2 euros per megawatt hour for both of the systems again. Additionally, and in the 275 megawatt case, moving from 8 to 12 hours has no effect on curtailed energy, while for the 500 megawatt system, the case is worse. Another investigation performed in order to estimate the effect of a hybrid RES energy storage power system on the operation of all the conventional units. The hybrid power system integrated for that purpose consists of approximately 1,700 megawatts of PVs and 275 megawatts of pumped hydro storage system. The variable input parameter was the availability of the pumped hydro storage system in hours, and results are here on this graph, where the daily average commitment span of for the different types of conventional units on the vertical axis is presented with the availability of the pumped hydro storage system for 0, 4, 8, 12, and 15 hours respectively. The group of bars for the 0 hours value is for the case where no pumped hydro storage system is installed. The main outcome is that the specific pumped hydro storage system has a significant effect on the operation of the conventional units, as it decreases the commitment span of their daily usage with many other side effects, such as lower fuel consumption. On the other hand, the pumped hydro storage system availability of over 8 hours seems that it hasn't any effect or any significant advantages. Now, following the previous developed approach, estimation of impact and implications of potential storage projects has also performed for an interconnected grid this time. The case was the interconnection of Cyprus with Greece and Israel, and the generator capacities for each country were used as main input parameter in the dispatched set model. Other crucial input parameters were the annual load demands for Greece and Israel, and the interconnector capacity, which have been taken as an assumption of 2,000 megawatts to and from each country. Results and output parameters have been concentrated again here in this table, and the important conclusions that came out are that there is limited risk penetration in case of no pumped hydro storage systems installation, and in order to accommodate the surplus of energy, leading to conditions where the goals posed are not achieved. Cyprus, on the other hand, would be energy exporter with larger RES share in case of a 275 megawatt pumped hydro storage system installation and interconnection, of course. And finally, the curtailed energy is practically zero by employing 700 megawatt pumped hydro storage systems, achieving marginally better unit energy cost, but also RES penetration and energy exports.
Dimitris, just a clarification, you mean 700 megawatt or megawatt hours?
Actually, it's energy, yes, you're right, it's No, the curtailed energy is practically zero by employing a system of a capacity of 700 megawatts. It's megawatts, not megawatt hours. The curtailed energy is practically zero as a result from our model simulations. Actually, the specific model simulations performed for installed capacity from 0 to 700. That's the upper limit, if we could say it like this, the 700 megawatt installed capacity, just to show the range of all of these changes.
Okay.
I think I can continue with conclusion summing up. To sum up with the conclusions from this presentation, and according to our results, pump hydro storage power systems can be coupled with batteries, as we heard yesterday, integrating an important potential to provide required energy services to the Cyprus grid. Moreover, there is significant room for such a hybrid power system to assist in achieving maximum penetration of available RES through PVs in particular. And finally, a hybrid power system of 1.5 gigawatts of PVs, together with 275 megawatts of pump hydro storage systems, may assist in achieving current and future goals for the electricity system, both in the case of isolated and interconnected Cyprus grid. Just to refer once again our SREC project as an acknowledgement, which is co-financed by the European Regional Development Fund and the Republic of Cyprus through the Research Innovation Foundation. And don't forget again to mention that the specific part of our work was also presented in the 14th International Conference of Energy and Climate Change, organized by the National Capodistria University of Athens the past month. And that's it for today's presentation. Thank you very much for your attention. I don't know if there will be or there are any questions, or we may have a general discussion at the end of every presentation. Ms. Kapouli or the other partners?
Haris Babachristophis has one question.
Yes.
Yes, actually, I have a few questions. The first one, you mentioned that you selected reservoirs based on having more than 40% of their water content. Do you mean that the water in the reservoir never falls below 40% of its capacity, even during years of drought?
Exactly. All of the assumptions used as an input parameter in our models have been made based on the worst case scenarios for water availability. So data of the long-term water availability of the reservoirs have been recovered for drought periods, and the assumption made was this, that the nominal autonomy of the system was calculated for exactly for 70% use of the upper reservoir water content. We used the worst case scenario in order to be much closer to reality, let's say.
So basically, I suppose the ultimate question is, if you design a system for, say, 10 megawatts and 10 hours autonomy, your assumption, based on the data you have for water availability during years of drought, would there still be enough water left in the dam in order to be able to give you that autonomy for your pumped hydro system?
Yes, that's the role of this assumption actually.
So you say assumption is...
That's the critical point here, that the nominal autonomy of the system was calculated for 70% use of the upper reservoir. And all of the simulations have been set for the drought periods as a worst case scenario.
Yes, so you ensure that on the low reservoir there is always enough water even during the droughts?
Exactly. Actually, these models are really dynamic. So dimensioning and sizing, of course, the result are based on these worst case scenarios for drought periods and for 70% use of the upper reservoir. Actually, this assumption has been integrated for that purpose, in order to acquire the worst case scenario, and of course for the water availability at the levels that we design and selected as input parameters.
And you found that there is a potential for 275 megawatt of pumped hydro, I assume with 10 hours autonomy even during years of drought.
Exactly.
Yes. What's the point of running studies with scenarios of, say, 700 megawatts of pumped hydro if there isn't the potential for so much hydro in Cyprus?
Yeah, exactly. But during model simulations, it's actually a sensitivity analysis parameter in order to see actually the range and actually here just to examine in what point the changes are occurred.
Okay, so basically
for example,
it's
500 megawatts as we referred, all of the parameters of the output parameters and the results remain almost stable. So
okay,
the greater the range of phenomenal capacity that we integrate in our techno-economic models, the safer the results.
Okay, so your point, the point you are trying to make here is not to suggest that Cyprus could go to say 500 megawatt of pumped hydro, but to say that you get most of the potential benefit even with 275, and you don't need to worry about the fact that you might not be able to go to a higher level.
Exactly. The 275 megawatt power system, according to techno-economic analysis and our models, and of course with the assumption and the input parameters that taken into account, is the optimum solution from both technical and economic point of view.
Can I add something on this? Because this was a discussion we had during the project. The reason we wanted to do a sensitivity analysis for bigger projects is because in the NECP we have included only 130 megawatt project as a forced investment in the system in order to accommodate more rest. So we have asked the consultants what will be the range of pump storage in case of Cyprus to go at a higher renewable penetration rate. That's why this exercise did exactly this. They simulated a lot of scenarios and they ended up that the NECP, the 130 megawatt we used in NECP is enough, but it can go even higher to 275, but it doesn't make sense to go more than that in order to achieve a certain penetration of renewable that it was suggested by this project, which it was around 50% of RES by 2030, if I'm not mistaken. Am I correct, George?
Exactly, yes.
If I may step in, I will show some information myself, let's say in the next slide, in the next presentation. Okay, so this capacity, let's say for the storage, okay, it is simulated as a pump hydro, but it could be also batteries and hydrogen. Okay, it could be a mix. Scenarios are there also for mix of storage, not only pump hydro. So don't be mistaken. Okay, the technology behind the storage it's a little bit different, but we would like to see here what is the effect of storage for an electric capacity provision. Okay, so pump hydro was the better alternative, but it could be also hydrogen. Okay.
Okay. I think we can continue the discussion at the end. We need to proceed with the presentations, so we can come to this topic at the later stage. We should now proceed with our next presentation. I would like to welcome Mr. Dimitrios Konstantinidis from Kalero. Mr. Konstantinidis, the floor is yours.
Thank you very much. Okay, copy. Just give me a minute to upload my presentation. So can you see it? Can you hear me?
Yes, Mr. Konstantinidis.
Okay.
Yes.
Yes, it's
Thank you very much. Okay, so good morning to you all and welcome to this web conference. Unfortunately, the pandemic has not allowed us to interact in person, but then again, technology supports us in order to communicate the project results to our interested audience. My name is Dimitrios Konstantinidis, and today I will present you some of our analysis results, focusing on meeting Cyprus' future energy demand by employing different set of renewable energy in Cyprus transmission system, employing also storage. So, following yesterday's presentations for electricity storage technologies and applications, I will start very briefly with a short reminder of in front of the meter storage benefits to the power system. Then I will discuss the aspects of the tool that we have employed for our analysis, the inputs and the simulation results for the isolated grid case and the interconnector case. George, in the previous presentation, he showed some part of this, what I'm going to show as well.
We cannot hear you.
Is it okay now? Can you hear me now?
We can hear you, yes.
Yes.
Yes, we can hear you.
Okay. So I proceed. What are the potential benefits of the electrical energy storage? I can pinpoint some here. It's for the user to increase the power quality, the demand charge management, for the generation to defer new power plant erection, and also this comes also for the transmission and the distribution system for congestion relief and for transmission upgrade deferral, and also for the dispatch of generators. So depending on the circumstances in a given electric supply system, energy storage could be used to defer or reduce the need to install new central station generators, or defer or reduce the transmission system upgrade needs, even though the latter is debated, as also stated by Mr. Taibbi yesterday. And Mr. Taibbi yesterday also mentioned arbitrage, which I will present schematically in the next slide. But these benefits for the storage, the electrical storage, comes when the storage system is the range of from 1 to 500 megawatts, and the target discharge duration is over 2 hours. On the other hand, apart from the transmission system benefits, let's say, on a political level, storage facilities contribute to the climate change mitigation goals that are set. And this is realized not directly but indirectly by facilitating the increase of renewable energy share in the power sector and avoiding unwanted energy curtailments and serving as such more green electrical energy. So what energy storage can provide is better scheduling and no curtailing for the investors, for the potential investors in the renewables. But of course, then again, this is with an associated cost, as discussed yesterday, that has to be faced by certain policies and measures that the states are developing now. And Mrs. Delenta showed some policies. So here are some visualizations of the previous statements for peak saving and load leveling, in order to avoid curtailment in the high renewables energy share. So what arbitrage means is that electric energy time shift involves the purchasing of inexpensive electric energy, which is available during periods when prices or system marginal costs are low, to charge the storage system so that the stored energy can be used or sold at a later time when the price or costs are high. Alternatively, storage can provide a similar time shift duty by storing excess energy production, which would otherwise be curtailed from renewable sources like wind or photovoltaics. Here you can see the light blue part over the demand, the green demand profile, and the orange one that indicates that no storage was there, would have been curtailed. So as a conclusion, let's say here, storage can accommodate further renewable penetration and help European countries to achieve their climatic change goals. Now, the EU, in order to facilitate the creation of such policies and measures and to support them, created a set of tools through the Joint Research Center. One of them for short time scale analysis is DISPACET, the tool that we have used. And there is another one for longer time scales, which is the EU Times that was mentioned also yesterday. So the DISPACET is a unit commitment and dispatch model that when run on a power system reveals the system's ability to incorporate effectively or not so effectively the production from the renewables. So the model is fed with information of the generators at place, the hourly demand profiles, the fuel and the ramping costs of the conventional generators, and the hourly intermittent generation production profile that is estimated for the renewables. Well, in the renewables with intermittent production, while for example, for biomass, this could be much better be predicted, the production. So the also constraints having to do with the operation of the generators and the storage facilities, the size of the connections between the systems, if there are there, are also inputs to the model, which has an objective to minimize the operational costs of the system and provide a schedule of conventional generators operation. Now, raw data are fed, as you can see in the right-hand side of the slide. Raw data are fed after they have been gathered from TSO or from other sources and elaborated upon, creating profiles in an appropriate format for the model to be used. A configuration file says the general characteristics of the simulation, and then the general algebraic model system, GAMS, is employed to solve this mixed integer minimization problem and retrieve the simulation results for the user. I was very happy to hear George yesterday and see Mr. Taibbi's presentation that another tool IRENA supplies now for the community is in place. So the Flex tool. It is always good for the researcher and the consultant to work with such tools, and why not build on them when they are open source, of course. So this DISPACET is how to say, a tool that was created from European Union that is very similar to what the Flex tool that Mr. Taibbi showed yesterday. So the model up to now has been applied by its main developers Kuolen, Kavadias, Pavisevich, and Zucker, in order to simulate the whole EU28 system, including the isolated transmission system of Cyprus. This was for year 2015. Then separately, the system of Central Europe, the Balkans, and specific countries like Belgium, Belarus, Bolivia, and the Netherlands, specifically for electric cars' impact on the Dutch transmission system. What's the effect of the EVs? What have we done here is that we have used the model DISPACET to check the requirements for achieving the RES penetration goal for the electricity sector. For the last decade, the penetration is shown in the graph below. The goal that is set on the National Energy and Climate Plan was for 16% for renewables for the electricity system, but as George Patasidis said yesterday, I think that this is now 30% for the electricity system. So in order to do that, there should be an exponential annual growth for new installations. And this should be mainly PVs because wind is not there in the island. And this exponential annual growth has to be sustained for the decade to come, up to 2030. Now we will see in the following that what is needed in terms of storage, where we have accounted for batteries, pumped hydro, and hydrogen, in order to sustain such growth, both in the case of isolated grid and interconnected grid. Our base scenario has been for 2019, where I have to tell you that from the TSO of Cyprus data, from the load duration curve that you see on your right-hand side of the slide, 2019 seems typical year for the decade of 2010 to 2019. So for this year, we had retrieved information and set up the profiles for demand and the renewables production, the water availability in the dams, the generator characteristics, and then renewable characteristics, and all other information required in order to set up the input for the model. So the simulation run, I have to tell you, that revealed a 9.8% energy from renewables as penetration for 2019, while the TSOC data for 2019 shows 9.7%. Of course, this is so because 2019 we have used real data. I mean, data that was there for the production and also for the demand. But we use this here in order to have the profiles for the 2030 and 2040 simulations that we have performed. So the future scenarios that we ran were based on the plan policies and measures, the PPM scenario of the NEC plan, with various additions of storage and renewables for 2030 and 2040, in order to reveal different situations that may arise, especially for renewable penetration goal. I will present more the 2030 case in this presentation. And concerning the electrical systems operational cost minimization, the cost parameters that have been taken into account are the same as for the simulations performed by other users using DISPACET, as I presented to you before. So fuel prices have been considered for the conventional generators, while no operational costs have been set for renewables installation. Startup and no-load costs have been taken into account for conventional generations, where ramping costs have been also considered for biomass. The main assumptions here for most of the runs that we've performed are the following. For example, for the isolated system of Cyprus, you can see that no transmission losses are considered, no outage factors have been used because there were not, how to say, the information was not there to use. You can see that the relatively low, for nowadays, CO2 price per ton has been used. This was 25 euros per ton. Yesterday, the value has been a spot price of 69 euros, and this is thought to reach 9 euros per ton in a year or so. These are some assumptions for the model's inputs. And also I have to tell you that there has been no installation or depreciation costs or a maintenance cost that has been considered for the simulations. So the scenarios set up and run for the isolated grid case are the following. You can see here in blue the scenario 1, which was for 2019. Then the yellow scenarios are for 2030, and a couple of scenarios here that are present in light blue for scenario 3 for 2040. You can see that the scenarios are based on the planned policies and measures scenario of the NEC plan, and they come with some variations. And here in orange, you can see the distribution of the conventional power generators and the renewables, and on the green side, whether the scenario has storage capacity or not. Some of the scenarios also had some variations on the fuel price that you can see in the table on your left hand above. But indicatively, I will show you some results. Let's say these profiles for the demand and the production and the scheduling, just for two cases. For scenario 2, which is the MMP scenario, and also the best scenario that we could find with having 267 megawatts of storage, and instead of 804 megawatts of PVs, a little bit more than 1,000 megawatts of PVs for 2030. And these are the profiles of 4 weeks during the year 2030 for the two situations. You can see that in the graphs below, which consider also storage, you can see that the energy that should be curtailed from the from the PVs is stored. So this is why there is something below showing this stored energy in the second case, where in the first case, in the scenario 2, there is no such capability. And just to compare these two scenarios, the RES penetration for 2030 with the assumptions that we have taken into account in the model, it's 20.7% for the PPM scenario and 27.5% for the scenario with more storage and more PVs. Now, in the table here, you can see some of the scenarios that we have run, which is in red. It's pinpointed the second scenario with the 27.5% of electricity penetration from renewables. And just to mention that for the scenario 3, which was for the 2040 year, a total of 37.7% of renewables penetration is achieved, but with additional 100 megawatts of storage as compared to the plan policies and measures scenario for 2040. Now, having said that, here, as George presented you before in his presentation, in order to be able to find out how we could capture the goal of 30% penetration for the electricity sector by 2030, we have performed another set of runs by assuming an amount of PV installations by 2030 of 1,680 megawatts, and then see what is the actual storage capacity that could support effectively, without any curtailment, this amount of PVs installed. And as George said before, we could create this graph showing that over 500 megawatts of storage, there is no significant effect, let's say, of pushing more storage into the system. Here, this was for the isolated grid. We have also collected some data for Israel and for Greece for 2019. Again, hourly profiles of demand and production. And we were based on this load and production profiles, and also some information on what is the planning of the two countries for 2030, and we were based on the NEC plan for Greece and some information of the Israeli Ministry of Energy in order to see how much amount of energy will be required by 2030, what will be the distribution of the generators and also the storage of these two countries. And here you can see these two scenarios that we have run. The only difference in these scenarios is the PVs that are installed in Cyprus by 2030, which for the first scenario is 750 megawatts PVs by 2030, while in the second scenario it's again the 1,680 megawatts for PVs. And you can see here that there are also storage facilities in place for Greece and Israel, which have been taken into account during the runs for the interconnector case, the Euro-Asia interconnector, as George Partasidis showed yesterday, this project. And the main assumption here is that all fuel costs and the cost of the ramp up, ramp down, and all the other costs of the generators are the same for all three countries. And we had created some scenarios for the transmission cost, with a low transmission cost of 5 euros per megawatt hour and 30 euros for megawatt hour, and see what are the differences. And for the first scenario, for the 750 megawatts PVs installed by 2030, it seems that Cyprus, in one case, for the low transmission cost, is not an exporter, it's a net importer of energy. And also for this scenario, Cyprus does not meet the RES penetration goals. So it needs more than 750, where of course 750 is, let's say, less than the 804 megawatt PVs that Cyprus has in the NEC plan to be created by, to be installed by 2030. But then again, it seems that if the installation of new PVs is not sufficient enough year by year now, probably the goal will not be attained. And the situation as we have simulated will be that Cyprus, when interconnected, will not be able to meet the RES penetration goal. When in the second scenario, as George said before, Cyprus will be a net exporter. Of course, the price, let's say, for the system cost, of course, will be a little bit more. But then again, the system cost is for the whole system that was simulated, which includes Cyprus, Greece, and Israel. And Cyprus is only a small part of this system, because the annual demand is 6 terawatt hours, while for Israel is estimated 95 terawatt hours, and for Greece over 60 terawatt hours. So just to show you this difference between the isolated case and the interconnected case. For the isolated grid of Cyprus, increasing storage capacity increases the renewables penetration, and in the same time decreases the energy cost, while during the interconnected grid, increasing the storage capacity decreases the RES penetration from a point over 275 megawatts installed, decreases net exports, and also decreases marginally the energy cost. But the energy cost is for the overall system of the three countries as a whole. So this is what I would like to present today. Thank you very much for your attention, and if you have any questions, I will be glad to answer them.
Thank you, Mr. Konstantinidis. As I've said, it's better to leave all the questions at the end, since all the topics are related to the project results.
Okay.
And for this, we can now proceed to our next presentation. I would like to welcome Dr. Melios Hadjikipris from Kalero. Dr. Hadjikipris, the floor is yours.
Thank you very much, Antonia. Let me share my presentation. Can you please confirm if you can see my screen?
Yes, we can see it.
So I would like to discuss today about dynamic time domain simulations of the Cyprus transmission system. Firstly, let me also welcome all the guests from my side. And it is my privilege to be a member of this research project, to cooperate with prestigious partners and fantastic colleagues throughout these 2 years work. So Initially, I would like to introduce, to discuss what is the scope, what is the research impact of this work. Then I will proceed with the fundamental characteristics of the Cyprus transmission system, which is the test bed system which we are going to test our proposed methodologies and techniques related with storage, rest penetration, and the hybrid synthesis of these two components. I will, of course, introduce what are the most suitable energy storage technologies for the autonomous island of Cyprus. Then I will introduce some case studies that we are considering for our simulation work, and then I will draw some conclusions. So the aim, the scope of this research work is to investigate what are the significant impacts, what are the great benefits that can be reached, can be achieved by this island, the autonomous power system of Cyprus, through the introduction of storage technologies, more specifically pumped hydro storage, where there was a big discussion since yesterday and today, with the support of battery technology, fast acting technology from battery, and how this through a synergistically synthesis with rest penetration, forming the hybrid storage model, can support the Cyprus power system. This will be tested and validated through some proposed hybrid power packs located across the whole span of the transmission system of Cyprus, and the effectiveness of these proposed schemes will be cross-validated through time domain dynamic simulations. So just a big overview, what is our tool? Let's say the test system. This is the transmission test system, which is the backbone actually of the electricity system of Electricity Authority of Cyprus. It comprises, of course, of high power, high voltage transmission lines, transmission substations, power stations transmitting bulk power from the power stations to the end load, to the distribution substations through these high voltage corridors. It transfers powers from transmission plant to another plant, or to transmission substations, or between substations, etc. This is an autonomous islanded power system, highly independent on imported conventional fuel, as well as the local generation from renewable installations across the island. Again, some technical characteristics. It consists of a number of transmission substations, 132 kilovolts and 66 kilovolts, which is the transmission level of the energy system of Cyprus, and also the source of energy, which comprises of three power stations across the island: Vasilikos, Degelia, and Moni power stations. These are subcategorized into steam turbines, which are operated as in a continuous manner as base load units, continuously operating to supply and to satisfy the continuous energy needs of the islands. We have open cycle gas turbines, which are in the intermediate level, intermediate units. And of course, we have the fast responding gas units, which are mostly operated for peaking high load periods, during the high demand periods. Also, we have some reserved units, as I said before, the gas units as well as internal combustion units, which are used in emergency conditions, also for black start actions. So for this research project, the way to test our proposed methodologies is through computer-based time domain dynamic simulations. So for this purpose, we're utilizing a high fidelity, high precision, full model of the Cyprus transmission system on a very trusted and well-used simulation package. This is Dick Silent Power Factory, German-based software package, which is heavily used by industries and by academia. So we consider that this test system serves adequately the aim, the scope of this research study for testing and assessing our proposed methodologies and testing the different scenarios through time domain simulation results. So, as we have already seen in these 2 days conference, we are converging towards storage technologies to support the needs of the island of Cyprus for reaching greater sustainability, resilience, and stability, and also in functioning in an autonomous manner, also to increase security as well. So through our studies, we have seen that a very promising solution to this problem is the utilization of existing water reservoirs across the island to be used as pump hydro storage services. This is a very trusted and reliable and mature technology utilized across the years worldwide. I was reading a few days back that this technology, which is widely used in Australia, they also call it the battery of the nation. This is a battery of theoretically infinite life cycles, and it only needs some basic maintenance of the generator, generation station, pumping station, and the pipelines, etc. In support to pump hydro storage, we have also incorporated in our studies some electrochemical battery energy storage systems to assist the service of pump hydro storage and to assist the performance of the system from the perspective of fast transients as a result of the inverter-based generation of the battery energy storage systems. They have a very fast response, fast action, which can ensure to preserve stability of the system, as well as to recover the frequency of the system in case of contingency and emergency conditions. So at this point, I would also like to shortly describe what we have seen in previous presentations. The hybrid synthesis, the hybrid solution that we have been discussing before, basically is a combination, is a synthesis of pump hydro storage consisting of an upper and lower reservoir. So hydraulic potential energy from the upper reservoir is flowing downhill through some penstocks, and the gravitational potential energy, which is converted into kinetic energy through the hydro turbines. The kinetic energy is converted into electrical energy. This electrical energy is directly supplied to the transmission grid for meeting the load, the needs of the load needs. So the photovoltaic solar power plants comes into play for two purposes. First, to provide energy directly to the grid, as well as to energize the pumps of the pump hydro storage to feed water back on the upper reservoir in order to have available energy supply in case of high demand periods. So this is a hybrid synthesis of the two. So the pump hydro storage provides electrical energy to the grid during high demand periods, let's say during evenings where the demand is high, and during the day where we have surplus of solar energy. The solar energy can energize during the day the pumps to fill up this battery of the pump hydro storage, let's say. So, as our colleagues Dimitris and George mentioned before, a serious feasibility study has been undertaken in this project, considering all existing water reservoirs across the island. So, as we can see on this table, it highlights a selection of the best 6 candidates which can be used for providing pump hydro storage service in the grid. A number of criteria have been considered: the percentual fullness, the capacity, the autonomy, what is the distance, the closest distance to a transmission substation, environmental issues, etc. So the total nominal capacity of these 6 water reservoirs is summed up into 275 megawatt. So this is a pilot and demonstration case, which we have focused in one of our examples. It's related to Kannaview region in Paphos, where we find a suitable location for an upper reservoir, as we can see on the top right corner here. We can also see the path of the penstock, the flow of the water to the lower reservoir. And on the bottom right figure, we can also see the generation and pumping station for this technology. So, as I have mentioned before, we support the operation, the service of pump hydro storage through some supplementary battery energy storage systems through their fast acting technology. So, we have, in this example, I have indicated the proposed batteries which can support, number one, the Kannaview pump hydro storage project, which we have seen on the previous slide. Also, another water reservoir, which I have included in the previous table, which is Kallopanagiotis, with its corresponding characteristics. And this battery, the second battery, is supporting the action of this of the second water reservoir of Kallopanagiotis. So, in addition to the pump hydro storage, the batteries will further support the action of the hydro plants during transient system periods through their fast switching actions of the inverters. This will ensure stability of the whole transmission system. So these are some figures of Kannaview. Kannaview is a very close region to Kannaview water reservoir, few hundred meters, which is actually supporting the action of Kannaview pump hydro storage technology. So before proceeding to the simulation results, let me introduce some scenarios which we have considered throughout this process. So initially, we are considering the basic scenario, the fundamental scenario, which, as we have seen before from my colleague Dimitris, we are considering 2019 as the reference year for our simulations. We are considering the real load demand and actual RES penetrations levels of the existing plants. These are solar photovoltaic parks, wind parks, and biomass, with their corresponding installed capacities. A future scenario, a first future scenario following the base scenario, will consider a penetration of photovoltaic technology into the grid, of a significant figure of penetration, while we're preserving the wind and biomass technology the same as the base scenario. We wanted to point out, to figure that the relative increase of solar penetration in the grid it's much greater as compared to biomass and wind. That is the reason why we have particularly focused on solar photovoltaic penetration. And the final scenario, we will see through the incorporation of storage, through hydro storage and battery storage, how this support enhance the performance of the whole system from stability, resilience perspective, as well as how it assists into the minimization of grid load variance of the system, and how storage can support an increase in RES penetration in the grid. Something which I have mentioned before, the time windows, the time series profile data are focused on the 4 seasons of the year 2019, which are focused on weekly profile data, as we have seen on the table below, for clarifying and comparing equally and evenly the simulation results across the whole reference year. So, as a first approach, we are studying just Kannaview and Kalopanayotis projects, along with their pump hydro storage and battery energy storage system, functioning in a cooperative manner. As I have also highlighted the corresponding water reservoirs on the table below. So, jumping into the simulation results, I would like to clarify what the legend, what we actually observe from the results. On the red line describes the base scenario, the existing load demand and RES installations of the grid based on the year 2019. Blue line represents the scenario of the increased PV penetration level, and the green line, it further incorporates the support of storage elements. So, initially we see, of course, as we expected, that the blue lines, which in a big portion of the simulations coincide with the green line, the blue line provides better performance as expected during day, where we have plenty of solar radiation and, as a consequence, plenty of PV generation in the system. So this phenomenon, it provides some sort of deloading relaxation of the conventional power stations. So then demanded conventional generation from the power stations is significantly less during the day. The impact of storage, so pump hydro storage, and to some degree the battery, is observed on the green line, providing load peak shaving during high demand periods, as well as load leveling during low demand periods. So during evening times, as we can see from the time domain simulations, energy is extracted from the storage elements, pump hydro storage and battery, into the grid. So flattening out the demanded power from the power stations. And during low demand periods where the energy is significantly cheaper, energy is extracted from the grid and consequently from the power stations to charge up the storage element units. So, as we can see from this figure highlights the demanded conventional power generation variation. What means is the average distance from the maximum to the lowest point of the conventional generation for all 4 periods. As can be seen, there is a significant reduction in the demanded load variance, which ranges from 48 megawatt for winter week up to the maximum of 118 megawatt during the summer period. So there is a significant reduction in the demanded load variance through the incorporation of these 2 hybrid power plants. So I summarize here the results of this first case. So the penetration of PV, it's obvious from the blue line, scenario 1, future scenario 1, which provide better results during the day. And the impact of storage element is reflected again on the figures on the green lines, where in most of the cases they demonstrate a substantial peak shaving during high load demand and load leveling during low load demand. So what means it smoothes out this mountain and valley effect. As a result of this, it minimizes the load variance, which enables the conventional power units to operate on their most efficient capacity. So, following this initial approach, which considers the 2 projects of Kannaview and Galopanagiotis, we are proceeding into the simulation analysis by considering all 6 proposed water reservoir along with the pump hydro storage technology, which were previously seen demonstrated below, summing up into 275 total megawatt into the grid. And how this the sum of these projects affect and support the complete transmission system of Cyprus. Again, we are running the time domain quasi-dynamic simulation results on Dix Island Power Factory, and we can see here a higher and a much stronger effect on the load peak shaving and load leveling of the conventional units, considering all 4 periods, the 4 different weeks across 2019. So these are some significant improvements made considering the sum of the pump hydro storage projects. This is also reflected from the bar graph, as we have similarly seen before, but here we can see a dramatic reduction on the conventional load variance, which ranges from 200 megawatt up to 280 megawatt. So this can be translated into cost of fuel, which is significantly less. We can actually utilize this storage element along with the rest generation to increase stability of the system, resilience, flexibility, which is also translated into savings. So finally, I would like to draw some conclusions out of this study. So the scope of this work was to demonstrate, to highlight the immense and significant benefits that can be obtained on any islanded autonomous power systems, but we are particularly interested for the Cyprus power system, of course, through the incorporation and utilization of the proposed storage elements, pumped hydro storage with the support of battery storage, which can be also synthesized together to form the hybrid power plants. From the results, we have also concluded the significant grid benefits through the minimization of the demanded conventional load variance, which as a consequence enables power stations to operate on their most efficient mode. In addition to this, through the incorporation of storage or the hybrid schemes in a closed corporation, closed loop form with the rest penetration, can contribute into the minimization of conventional units required for idle operation. What means? Steam units which are heated up, which are ready to be integrated in the system in case of events or emergency, but actually they are burning fossil fuel without being actually integrated in the system, connected in the system. So these can be actually substituted by these hybrid schemes. Also, these hybrid schemes can also assist in avoiding the deployment of new power stations. We have seen that, we have concluded also that the incorporation of storage in the grid enable higher PV penetration in the system, which ensures that the discontinuous nature of RES, the intermittent nature of RES, can be stabilized through the incorporation of storage. So it's actually assisting the security, increases the security level of the whole system. Last but not least, the simulation results have proved the effectiveness of the proposed storage schemes and how this can actually comprehensively support the autonomous power system of Cyprus in reaching higher penetration levels, greater flexibility, resilience, stability, and how this builds into the overall performance optimization. So some key findings out of this research work have been submitted for publication on a high-impact journal paper. At this point, I would like to thank you very much for your attention, and I will be happy to address any questions.
Thank you, Dr. Hadji-Kipri. We can now proceed to our last presentation of the day, and then the questions will follow. Our last presentation would be co-presented by Dr. Athanasios Katsanevakis from Kalero and Mr. Hubert Geisberger, excuse me if I don't pronounce it correctly, Head of Sales, Voice Group Division Hydro. Dr. Katsanevakis, if you want to start with the presentation, and then we shall proceed.
Thank you very much, Antonia, for calling me in this conference. Let me try to share my screen here. Something's going wrong with my share mode. Take some time to load the presentation, I think. You actually see now the screen or not?
You can see the screen. Yeah, you can see the presentation now.
You can see that, okay. Because the loading was a bit difficult, I tried to open the screen from my computer. Is all right?
It's okay now.
It's all right now? All right, thank you. So the point is there is some infrastructure in Cyprus, and how can we use that to achieve better conditions and flexibility in the electricity market? And that means altogether RES penetration increase, lowering costs and everything. So most of the material has been already presented by the previous presenters, and however, what I want to point out here is that we are very lucky in Cyprus because we do have infrastructure which can help and very much in the transition to a more to more renewables inside the grid and lowering the cost of our electricity in Cyprus. So this has been also said before, but we'd like to stress this out because that makes a huge benefit for Cyprus. And if we strictly talking right now, we do not have any storage in Cyprus. Okay, we are based very much on conventional fuels. We have achieved a 13% of electricity penetration by renewables, and we do have some renewable sources which do exist in plenty of them, like the solar irradiation, and we need our conventional units to cope with huge load variation, also during the day and during the season. And that comes out from the figures which were presented by previous speakers, and related also with the change of the population of the island due to tourism during the summer period, and also because of the operation of heating air conditioning units all the day around and so on. So we have to face some significant variations which make as proved and shown by the previous presentations important to achieve stability and lowering costs of energy and improving actually the condition of the electricity grid in Cyprus. Several of the parameters to be considered are that we need storage. We need that storage for several hours because the profiles of demand and generation of energy show that, and that has been proved also from the analysis taking place during the course of this project. Another parameter which should be taken into account, and it is very important, might be much more important in the future, is the environmentally friendliness of the methods of storage to be used. Because we talked very much about the storage possibilities and technologies, that not only of them do have a environmentally acceptable footprint, taking into account their lifetime, the disposal of the equipment at the end of life of their lifetime. What is the lifetime of all these storage technologies which have been presented up to now? This is the environmental parameter is a parameter which should be carefully assessed now, because in the future that might become a huge problem. And then we have to go to the operational parameters, which is the pilot operation of the storage technologies and units with the existing conventional units. And of course, something which is very, very important is the commercially proven capability of any storage technology to be applied. We have seen that table before, but this is, I would like to stress the importance of this table. Is an outcome of this project, and what it says to us is that, hey guys, don't try for 12, 15 or so many hours of storage, because even with 8 hours storage capacity, we can achieve both renewable penetration, and we can achieve both lowering costs. All right, so more than 8 hours of storage capacity does have a very marginal role on these important parameters. So I'm just saying you, what we discovered during the run of this project, that during initially we were talking about 10 hours, 12 hours, 15 hours of storage capacity. Now we're talking for 8 hours. And what is the importance of that? It is that if we talk about 8 hours, then we can increase considerably our storage capacity of the proposed storage technologies. And this will be obvious in the next slide. But with this slide, I would like also to stress the effect, which is also an outcome of this project, the effect of the total installed storage capacity in terms of RES penetration and cost of energy. So at a range of 270 megawatts, we achieve 39% of RES penetration. By increasing this to about 500, we can increase also the RES penetration, lower a bit the cost of energy, the unit cost of energy. So what we're talking about, which is very crucial for the future development of the grid, is to achieve a installed storage capacity of about 200 to 300 of megawatts. This is an important outcome of this project, and we'll use that afterwards. And also to stress out the importance of this figure, which has been also presented before, is that by using the storage capacity, that permits us to increase the installation of RES power plants in the island. Otherwise, we cannot, because the grid as it is right now cannot support that. And by increasing these RES power plants, okay, in that figure, the PV's RES plants have been increased to 1.5, say about the gigawatts of nominal power installed. But taking also into account the storage capacity we saw in the previous table, what we achieve is to reduce the up and down limits of the conventional units, based on oil actually right now, by 150 megawatts. And just to mention something which came out from the previous presentation of Melios, is that actually when we install a plant which has a storage capacity for 8 hours, of course, okay, of a nominal power of 100 megawatts or of a nominal power of 200 megawatts, we actually do not need to have ready for operation a conventional power plant of the same, more or less capacity, which says at the end of the day that by installing only storage power plants in Cyprus, we can avoid building new conventional power plants in the island. Okay, this is something very important that has to be taken into account also by the policy makers. So having that in mind, we visited and we take into account all the existing reservoirs which are in Cyprus, and these are many. There are many water reservoirs in Cyprus, and that actually this idea came many years ago, but under the Restart project was able to put in work actually. And there are a lot of many reservoirs around. Many of them, some of them are huge, and the idea was, oh, why not use them as at least low reservoirs for storing power plant. And we try to select some of them and rank. The ranking order has been already presented, and we finally found several of them which are well suitable to be used in a future project of having storage capacity in Cyprus. And the table of all of them is shown here, and here is shown the capacities, but under the point of view that only 8 hours of storage capacity is needed. So you can see that we have a considerable increase of the storage capacity which could be available by only 5 of them. Okay, the most, say, suitable in terms of contents of water during the dry period and so on. What the discussion has been done also yesterday and also in the morning, but we can do that afterwards. And we already have more than 300 of megawatts of possibility for storage capacity if we talk about pumping storage systems. And why we're talking about pumping storage systems? We do that because for the quantity of energy we need the storage, which is 8 hours, for less hours, we saw from the analysis that we do not achieve nor renewables penetration, nor lowering of the cost. So for the hours we need the storage, the power, which finally comes out with a storage capacity of hours, the important point is the 8-hour storage capacity. So the technology which can be used for that nowadays and which is commercially viable and acceptable and so on is actually the pumping storage. And we have the privilege to have here a colleague from the pumping storage industry, which will take the stage after me to make us a bit more familiar about the concept, the technology of pumping storage, because, you know, battery is something of the everyday life. We have batteries in our phones, in our everywhere, but we are not so familiar with the pumping storage technology. So we have an invited speaker here in this conference to try to make us a bit more familiar about this pumping storage technology. So the priority projects are those 5 projects I mentioned before and are shown here on this map. And all this together makes up a sum of more than 300 megawatts of storage, which is enough for the next coming, say, 2 decades in Cyprus for benefiting the grid system and of Cyprus and also the consumers of electricity in Cyprus. So actually, from all these projects, we selected one, the Canaview project, the Canaview Reservoir, and here are some of the main features of this project, which can be used as a demonstration project. And we can have a view here where is the project located. We can see the penstoke, the upper reservoir to be built on a hill upwards of the existing Canaview reservoir. You can see the batteries located in Anaview area, which is close, as Melio said before, to the pumping storage project. This is a battery storage project, and those two is planned to collaborate in order to achieve also the stability needed of entering and out, the enter and out of the pumps in the grid. Okay, and you can see here some artistic view of the turbine and pumps building nearby the existing lake of Canaview, and also the upper reservoir to be built. You can see the upper reservoir here, and down there you can see the existing Canaview reservoir. I'd like to let the stage to Mr. Geisberger from Voigt Group to, as said before, to make us a bit more familiar with the pumping storage technology. Thank you very much for your attention.
Thank you very much. Then I will take over and try to share my screen. 1 second, please. Okay. So my name is Hubert Geisberger. I'm working for Voigt Hydro in Austria. It's a pleasure for me to join this conference and to give you some more insights about our company and also about the pump storage technology. Is everybody able to see the screen?
Yes, we can.
Yes, it's all right.
Yes.
Thank you.
Good. Brief agenda. As said, I want to introduce our company shortly, give a review of the energy situation, as some of the speakers before has already given, then why we come to pump storage, and insights in the technology. And at the end of the presentation, I have prepared some references of pump storage projects. So Voigt, some figures about Voigt. We are about 20,000 employees all over the world, stationed in more than 60 countries with 90 nationalities working for us, active in 5 markets from energy, transportation, marine, raw materials, and also paper making. We have an annual turnover of 4.2 billion, and we are engineering a technology-driven company, which reflects in our spending in R&D of about 4.5%. And we are family-owned since more than 150 years, in Germany based. So hydropower is a major contributor to the sustainable energy production, as there's no carbon CO2 footprint. And currently it's above 60% of the energy produced out of renewables by hydropower. And out of this hydropower produced, about 1/4 is running through turbines and pumps produced by Voigt. We consider us as a full-line supplier from water to wire for the electromechanical equipment. Means we can supply from turbine, generator, up to the high voltage line, everything which is the equipment for the power station. We cover the entire life cycle from the planning phase till manufacturing, installation, and also further on service and refurbishment after years of the operation. Voigt Hydro is active, as said, worldwide, and on this slide you can see all our operating units all over the world, where we are close to the customers and close to the big hydro markets currently. As said, I'm stationed in Austria and working basically in Eastern Europe and in Southern Europe. Some references over the last 150 years in hydropower. So we participated in Niagara Falls, for instance, units running since more than 100 years. They are not used anymore now for regular production, but they still can run and can produce electricity. Nowadays, they have bypassed this and have installed new units. I don't want to bother you with all the stations we participated. Just some major ones. This is Three Gorges, the biggest hydropower station in the world in China. Wudongde, for instance, the biggest installed capacity per unit with about 800 megawatt. Pradesh 2 in Portugal, Europe. It's the biggest variable speed pump turbine in Europe. And also recently we got awarded for Snowy Hydro, Snowy 2.0 in Australia, which will be one of the biggest pump storage plants in the world with a capacity of 6 times 300 megawatt. So we have the leading edge technology in-house to do all these investigations and design works before we go to the prototype. So for instance, on the left-hand side, you see a simulation of a CFD, computer fluid dynamics. And on the right side, you see the simulations about the electrical and thermal behavior of stator bars and components in the generator. So I shortly come to this energy situation in Cyprus. I've seen that the speakers before have stressed this very much already. Just it is seen now that there's not so much renewable contribution yet in the system, but it is expected that in the future, wind and solar will dramatically increase. This brings us now to the point where we see why we need pump storage. So in the past, the grid and the energy production was basically driven by big stations located in central locations of the countries, basically coal, oil or gas systems, transmitting the energy to the consumers, either to the households or also to the industry finally. And in the recent years, the renewable energy generation increased significantly and contribute to this grid and energy production. The problem with this renewable energy is that it's very volatile and it's not really predictable and forecastable if the wind will come in 2 weeks or the wind will not come, or it also could be that there's a cloudy or foggy day in winter times where no sun is coming, so you need backup systems. This is very crucial for these thermal power stations because they have a rather long lead time to build up or to decrease capacity. But this is the point where pump storage comes into the picture. Pump storage on one side can store the energy, which is produced in the grid, and also can relieve it then on demand. And this not only for days and weeks, but also can react very short within seconds to balance the demand and consumption in the grid. And in the future, we'll see that also when we look at the climate goals, there's a CO2 reduction required in all of the countries, which would mean that this big coal, oil and gas units will be shut down and will not be replaced. And currently they are supplying a big inertia into the grid, kind of spinning reserve, which also helps to balance the grid situation. And in the future, when you have only this photovoltaics and wind in the grid, you do not have this rotating mass in the grid to balance it. Also on the consumer side, we have seen in the recent years, in the past, there had been big motor consumers with rotation, with inertia rotation. But nowadays, biggest consumptions is coming from, for instance, from HVAC systems, means from climatization systems, which do not have possibility to also somehow balance the grid situation. And pump storage Units also have therefore a big inertia to support the stability of the grid. As also partly said by some of the speakers before, there are 4 big difficulties seen in the grid balance, or how to balance the grid to run a stable system. In this graph, the blue line is showing the demand over 1 month in area Germany with the daily fluctuation. And the green and the yellow part, the fields, the areas below, the green is showing the wind, the actual produced wind, and the yellow part is showing the produced photovoltaics. This section is from, or this part is from winter months, so the solar production is not that big. But with these 4 highlighted fields, we can see that there are certain demands where flexibility is needed and cannot be given by the current energy systems. For instance, it could happen that the wind energy is so high that it's exceeding the current demand. So you need something to stabilize the grid or to take out that energy. Here you have the possibilities of pump storage or also using even battery storage. The second case is that the wind suddenly increase very much, where you have very steep curves of this. And as said before, thermal power systems cannot follow such steep demand changes because they need a longer time to react on the requirements. Third factor could be that for a longer period, basically it's in Middle Europe, it's in the winter time, when you have low wind and low photovoltaic energy produced, that you need something to cover up this energy demand, lack in demand. Furthermore, also the wind has the problem that it's not really predictable. In this section number 4, it is seen that it was expected higher or lower wind, and you need something to balance. And this is the place where you need the storage systems. So let's have a closer look on the pump storage systems. So at a glance, such pump storage systems can operate and produce from standstill to full power in around 90 seconds. Smaller units can do it even faster. Basically, it's not really driven by the unit, but it's more driven by the waterway and the water reservoir settings. Unit powers are possible from 180 kilowatt or up to 500 megawatt per unit. This needs to be, of course, adjusted to the specific needs. And as said by the colleagues before, in Cyprus, some units with about 40 megawatts are considered. A special advantage, which maybe is not really always looked on when you look at the investment, is the design lifetime. Such units and power stations are designed for a lifetime of 80 years without major changes or repair works. Of course, for part of the equipment, you do some refurbishment, but basically, when you invest in such systems, you should consider it that it's running for 80 years. Voigt has installed now more than 500 units already all over the world. And we installed the first pump turbine in 1908. Actually, it was in our mother company in Germany, where we introduced an upper reservoir artificially to test our equipment. And it was considered as the first pump turbine installation. The principle, I think it was already explained by some speakers before. When there's high power in the grid, you will consume the energy with the motor generator and the pump turbine and pump the water from the lower reservoir to the upper reservoir. And when there's high demand in the grid, you will do it the other way around. It means you will relieve the water from the upper reservoir through the turbines and produce electricity which can be supplied to the grid back. A scheme of how such a system looks. So on left top, we have the upper reservoir with the dam shielding the water. Then we have the penstock and the waterway systems going down to the unit. You have an inlet valve, which is shutting off the unit in case you don't need to operate it. Then the pump turbine itself with the number 4, motor generator 5, and also the systems around, like the switchyard and transformers you need to connect to the grid. Some showcase of the developments of the sizes of the units. It is seen on this slide that since the beginning, since hydropower was introduced some 150, 160 years back, the unit capacity was rather low. And since the 70s and 80s, it was significantly increasing, that there are units now capable to operate at 1,000 megawatt. As said before, this is Wudong-Ge project in China, which is the biggest installed unit. This is for the Francis units, and we see for pump turbine units that we also are now in a range of up to 500 megawatts, with some supplied units by Voith, for instance, in South Africa, in Angola, or also Limburg in Austria, which is about 240 megawatt per unit. The application range of such pump turbines is shown in this graph. So on the bottom axis, on the x-axis, you see the output power, and on the y-axis, you see the head. So depending on the head, means the head level is the difference in the water reservoir levels between the upper and the lower reservoir. You would use a certain application. For high head differences, a ternary set would be the proper solution with a multi-stage pump. For lower heads, you can easily use reversible pump turbine units. Just an overview of the comparison of the ternary set. I didn't explain before in detail. So actually a ternary set is a motor generator connected to a separate turbine and a separate pump. This gives the advantage that you can cover bigger head ranges, and also, as shown below, some more details. Nowadays, when you look typically on the investment, you will use a system like on the right-hand side, where you have a conventional reverse pump turbine with a motor generator. So the differences are shown below. Such a pump turbine would be, from the investment point of view, cheaper compared to a ternary set. Also, the space requirements is lower because you only have two components to be installed. On the other hand, you would have lower efficiency, also have difficulties with the setting. Setting means the level of the pump below the lower tailwater level. It is because of cavitation and physical limitations that the unit typically needs to be below the lower tailwater with about 1/10 of the overall water level difference. This means if you have, for instance, 200 meter head difference, the pump turbine needs to be about 20 meters below the lowest tailwater level. Hydraulic short circuit would give some more flexibility, as shown on the next slide. And the operational cost and the technical risks, of course, are less with a more simple solution of the pump turbine. Here on this slide, I show you some pictures and the reference of a ternary set. It's an installed unit in Kops in Austria, close to Switzerland border. There is a 3 times 175 megawatts. And on the top, there's a Pelton turbine, which is connected with a motor generator. Can you see also my cursor, I assume, yeah? It's connected with a motor generator, which again is connected to the pump. In this specific case with a hydraulic torque converter, which gives additional flexibility to the overall system. And the specific thing on this ternary set is that you can run normally in turbo mode, water is coming from upper reservoir. passing through the turbine, producing energy. And in case of pumping, you will use water from the lower reservoir, put it through the pump, through the penstock, and bring it back to the upper reservoir. And for this ternary set, you have the possibility also, instead of using the full water flow to the upper reservoir, give a certain water flow back through the turbine to also be able to optimize the power consumption. The topic with the normal pump turbines is that in pump mode, you do not really have regulation flexibility for the pump capacity. So it's a on-off thing. So for instance, this Canovio, if you have a unit with 40 megawatt fixed speed solution, you would only be able to either consume 40 megawatt or produce 20 to 40 megawatt, but the area in between you cannot really cover. And therefore this hydraulic short circuit brings flexibility. On the right-hand side, there's some pictures. In this case, is a multi-stage pump, which is used here to cover the huge head difference. So here it's in the photograph of the installed unit, and you can see the section drawing. Here, a further example of, let's call it standard pump turbine solution, where you have the motor generator on one side and the pump turbine. For the turbine mode, the unit spins in one direction, and for pumping, you need to change the direction of the revolutions of the unit and to pump the water up again. Here we have an example from the States, a Basque Country with an input power of 410 megawatt. So these pump turbine solutions with fixed speed have the certain topics, as said, where they have limitations. So the variable speed pump turbines comes into consideration. There's some disadvantage also for variable speed pump turbines because they have a high investment cost and also have a larger complexity, which means in the end some more servicing efforts and maintenance efforts. But why it's typically used variable speed? The basic motivation is to control also the pump power. It means that you don't have only the possibility to have on-off in pumping mode, but you also have the possibility to control the pumping input power in a certain range. There are several other needs for variable speed, but they are not so dramatic as the pump input power variation. For instance, a large head variation in the reservoirs could also require a certain speed variation to have a stable unit and stable operation. And also when it comes to performance and extended turbine ranges, also a variable speed unit will give you advantage. And another feature is to also support the grid stability, because if the unit is running in a certain operating mode, by these adjustments on the electrical side, you can easily show to the grid a fast response in regard of power consumption and also in regard of the power production. An example of a variable speed pump turbine is the Frades 2 power station in Portugal, owned by EDP. We have for it delivered the entire electromechanical equipment as shown in this sketch on the left side. And here the specific thing is the power regulation in pump mode, which is between 320 megawatts to 430 MVA. As said, for it delivered the entire equipment. And we have seen before the sketch of the pump turbine unit where you have the motor generator connected to the pump turbine. And here on this sketch, we can also see the additional equipment needed to make the units in a variable speed operation. Some speakers also stressed already the topic of battery storage. And here I want to give an overview or an application range of pump turbines versus batteries, or where both systems actually can coexist and cooperate together. So on the x-axis, you see that the time scale. It's starting from microseconds, seconds coming to days and weeks. And we see here that batteries have good application ranges coming from very fast response up to minutes or maybe some hours of storage capacity. Of course, it's not one battery type system you can use for this entire range. When you come to this very fast response time, it's maybe some capacity systems. Lithium-ion accumulation systems would be somewhere in this range, and coming further to days and hour, minutes and hour storage, it would be maybe type of redox flow. And here in this light blue color, we see the application ranges of these pump turbines, fixed speed and vast speed. So they both have also a rather short time frame needed for reaction, but on the other hand can also store and produce energy for hours, days, and maybe also weeks, depending on the water reservoir volumes.
Ναι. Μια χαρά να μαζί.
So we see a good possibility to integrate pump storage and to enlarge the flexibility of pump storage systems with battery storage systems. Specifically, the advantage is that you could share the infrastructure. You can integrate it easily into the control system, which can allow use both systems in an optimal way, and also allow more flexibility to the pump storage capacity production. And we as Voith also can integrate these systems. We have in-house, in our sister companies, some lithium-ion battery systems, and also some redox flow battery systems, which can be good combined with pump storage on a larger scale. Just a showcase why we see that this pump storage and battery systems can good cooperate. On this graph, it's shown the energy production and energy demand in South Australia. You may be aware that some 2 years back or 3 years back already, there was a major blackout in the system in South America. And here on this graph, you see the different production and different wind, photovoltaics, and also gas production. It's shown over several days. And then after this blackout, you may have heard that the Tesla founder, Elon Musk, supported the Australian government and placed the biggest battery storage system, which is that time. So it was 100 megawatt with a storage capacity of 129 megawatt hours. And he placed it very short. It was published all over the world. And here in this black right angle, or this black square in the middle, you see the capacity versus the consumption and production over the weeks. So you can see that this is a rather limited contribution, but of course it is supporting the grid. And now the Australian government further developed the systems and the implications of all these electrical consumers and producers in Australia, and introduced now the Snowy Hydro 2 pump storage system, which is currently under construction. And this is, as said, one of the biggest pump storage systems currently under construction in the world. And the black rectangular now showing the capacity and also the output of this system can add to the grid. So it easily can cover the entire consumption in South Australia for 1 week. Also store the energy produced by wind and photovoltaics. Some references. as said, Voith already supplied pump turbines and contributed to pump storage projects all over the world. And this slide we show some of the major projects we did from the United States to South America, also in Gula in South Africa, Snowy Hydro 2 now in Australia, and a lot of units in Europe and in Asia. I just pick out some selected projects which we did in the last years. There's REC 2 in Austria, which 2 times 250 megawatt. Specific here was a rather high head difference of almost 600 meters, and it was commissioned in 2014, where Voith supplied the 2 pump turbines, including the governing systems for the customer Verbund hydropower. Another example and reference is Sirbishi. It's in Iran, where Voith supplied 4 pump turbines, including motor generators, the governing system, and also the valve system, including the electrical balance of plant, for 4 times 260 megawatt. The customer was Farab as the general contractor there. Another contribution of Voith was the pump storage plant in Geildorf. This could be also very interesting, probably for Cyprus. So the specific here is that you see on this upside of the hill, you see 4 windmills. And a closer look of the windmills during the construction is that there also was constructed a water reservoir around the tower of the windmill. And here you see the lower water reservoir. It means that there is also installed a pump turbine. During high wind energy production, water will be pumped up the hill to these reservoirs around the windmill and relieved down to the lower reservoir in case of low wind production and produce energy for the grid. As said before, so water is pumped up to the lower reservoir to these reservoirs around the windmills and relieved in case of low wind production. Sorry, I skipped this slide. So as said, such pump storage applications will have a long time for operation, as said, more than 80 years. And Voith is also taking care of the refurbishment and the rehabilitations. For instance, here we see this Festinok power station in UK, where the units are in operation since roughly 50 years. And Voith is now making a rehabilitation and supplying some components new and increasing the flexibility and the capacity of this unit. So at this stage, I want to thank you for your thank you to the audience for listening to my presentation, and give a hint that you also can follow us on the social media. And I'm now welcoming your questions.
Thank you, Mr. Geisberger. It's now time for our discussion. So anyone who wants to do a question to any of the speakers, they can raise their hand now. Mr. Michalis Papachristophis.
Yes, I will start with a question to the last speaker. I assume that variable speed turbines will not be providing any inertia because it will be behind converters. Is this correct?
It's depending on what type of variable speed systems you're using. So, for instance, if you use asynchronous motor generators, there you are directly connected to the grid. But also in this case, as you mentioned, when you have this type with the full converter units, you also supply inertia to the grid, because still the units are in operation and spinning, and they have the inertia inside the generator, basically. Yeah.
I was under the impression that generally generators behind converters like wind turbines, for example, they don't provide inertia because the converter won't allow them to provide inertia. And I know that the virtual inertia has been in discussion for a long time, but I'm not aware of something commercial where a converter is providing inertia.
Mm-hmm. It's not the converter providing the inertia, it's the spinning unit. But maybe we can take a closer look into this example because I'm not the full expert of this electrical side, to be honest.
Yes. Can I also ask a couple of questions to this? I think it's the second and the third speaker. We are shown some tables with unit costs for different options. My question is, those unit energy costs, do they also take into account the capital cost in order to build all the infrastructure that is being proposed, like the pump storage or the battery units?
Mr. Papachristophis, it's Konstantinidis. If I may answer your question, no. I have said in my presentation that installation, depreciation costs, and maintenance, overhead and maintenance costs are not, let's say, taken into account in the simulations. And this may be very useful, let's say, when you have a simulation horizon of multiple years, for example, for depreciation, because you have to take all the generators into account. No, but for our purposes, that we have to schedule just for 1 year, let's say that we shown, we have not taken into account these costs.
Well, but then how can it be valid to claim that as you install more megawatt of pump storage or of longer duration pump storage, the energy cost will fall? Yes, maybe the fuel costs will go down, but the energy cost that the consumer will pay, it could actually be increasing because of the billions that will have to be spent in order to build that infrastructure.
Look, yes, these, let's say, models present some information about how the system is going to operate, but without taking into account all cost that is introduced. So it's not a quantitative, let's say, analysis, because we don't know a lot more. We don't know the fuel prices, for example. We don't know how many generators are going to come into place and installed at a certain point from today up to 2030, for example. Okay, so if one introduces all this information, then the scenarios are, how to say, develop exponentially, the possibilities. You know?
Have you provided, because I don't seem to remember anywhere in your presentations providing an estimate of the costs in order to build the storage that you propose. It's a bit misleading. It's a bit misleading to show decreasing costs as you go from installed capacity of 275 to 500 megawatt of hydro storage, or as you go from 4 to 8 to 12 to 15 hours. When you don't take into account how many hundreds of millions or billions it would cost to build all that.
May I enter the discussion? This is Thanasis Katsanevakis. May I enter the discussion between Michalis and Dimitris?
Of course, please.
Thank you. Actually, the business models we run during the course of these projects show that there is no reason for any funding, state funding, for the storage plants to be built if market actions will be taken into account. So the consumer will not be charged with extra costs. First. Secondly, the billions that were mentioned before is not billions, it's just millions, and is well compared with the cost of new to be built conventional power stations. So, of course, what Mr. Papachristophis says, actually to take into account also the investment costs and all the depreciation costs and things like that is something which can be done. But in that stage, what we did is to have a basis to compare different scenarios of interconnection things, storage things, and so on. Of course, the investment costs and the depreciation costs can be taken into account. They have been taken into account in the specific projects, demonstration projects we are developing within this project, but and show what I said before, that the cost of these storage plants is well comparable to the cost of the new to be built conventional units which are needed. So the effect on the final cost of the consumer is neutral.
Okay, can I proceed to the next question? I think this was in the second presentation where you showed some results with the interconnector. I find it very counterintuitive that with the interconnector rest penetration actually reduces. Why is that?
Well, this is what it was troublesome for us to understand this, but this is the case because some of the energy is interconnected between from Israel to Cyprus and from Cyprus to Greece. What is the penetration? Is the rest penetration only for Cyprus? Okay, is the renewable energy produced in Cyprus? Okay, against the other energy produced. So means that one has to take into account all the interconnections and the transfers between the three states, not only for Cyprus.
So what you are saying is if because you have the interconnector, you still have the same amount of rest production in Cyprus, but you have less conventional production because you replace some of that conventional production with imported energy. It will show in your results as a decrease in rest penetration for Cyprus, even though in fact the rest production hasn't decreased. Is this what you are saying basically?
Well, you know, the system now it's not only for Cyprus but also for Israel and Greece, and the conventional generators there, the storage there, and also the renewables in those countries also play a role on what will be the amount of electricity generated in Cyprus. Okay, because some of this is transferred, and what I've shown for the net transfer is that more power is exiting the island than entering the island from the interconnector. But as the storage increases, this power transferred decreases. Okay. These are the results of the simulation.
So, for simulating the flows across the interconnector, did you use some assumptions, or did you use a tool which takes into account basically does a unit commitment for the three countries together? How did you do?
Israel has been, let's say, connected only to Cyprus with one cable, and this cable has some limitation on the capacity, and this was taken account in the software, in the tool. And from Cyprus to Greece, there was another, cable that has a certain capacity. The thing was that for Greece, because Greece is within another interconnected grid, the historic, let's say, net transfer capacities from to other European countries have been taken into account. So let's say that Greece has been, let's say, like a pump for power, for energy. This we have seen that. But no other constraints, let's say, or something has been taken into account for the interconnector between the states.
So, what I'm trying to understand is how did you arrive to the profiles for the energy flow along the connector? Did you do some kind of, did you say tool that does some kind of an optimization of, like you did economic dispatch just for Cyprus? Did you do something similar for the whole three countries in order to arrive to the flows between the three countries?
Yes, you're exactly correct, because the system in that case was not only for Cyprus. What I've shown you was only for Cyprus, but similar, let's say, findings you can find for Israel and Greece separately. Okay, as in EU 28, the example for this passage for the whole EU, or the Central Europe, or the Balkans, you just describe the possible interconnections, okay, their capacities, and then the system, depending on the costs that you have used, let's say, between the countries, you can specify different costs. Costs can be, the fuel cost could be, let's say, changing every hour with an hourly profile between countries. Then the system takes into account as a whole the states and solves for minimizing the cost. And this is why the cost, let's say, the unit cost has been reduced so little. If you remember for the 30 megawatts per hour cost case for the interconnector, very little, because the system is much larger. Okay.
Okay.
So the effect of storage in Cyprus only, by changing only this parameter, did not have so much effect, let's say, on the overall system.
Okay. This tool, Dispasset, does it also take parameters such as mass run units into account in order to ensure that the solution that it gives is viable?
Look, whatever, let's say, whatever you can describe mathematically, it can be done. It's not done now. Okay, it's not ready to do that. But because it's a GAMS, let's say, environment, you can provide equations, let's say, in order to be taken into account as well.
So just to be clear, the results that you have shown, they don't take into account the fact that Cyprus needs to have a minimum number of generators in order to ensure that if one trips, then you don't lose the system.
Look, this PPM scenario had some, some generators. It was a new combined cycle generator, and all the old ones that said that will be remaining up to 2030. Apart from those generators, we have, how to say, made some scenarios for additional PVs and additional storage without taking out any generators that are not, how to say,
yes, but when we do market studies for interconnectors in European organizations, for example, one of the parameters the simulation tools take into account is must run units. The fact that you need to have, at any given time, you need to have a minimum number of generators in operation, which means that you need to have a certain number of megawatts coming from conventional units. And this is needed for the stability of the system.
Okay.
Did you take this into account in this facet?
No, let's say that we don't. But how about 2050? How is it going to happen then without any conventional generators?
Well, with today's technology,
yep.
This is necessary. If in the future some other technologies come and are able to provide inertia and and dump energy quickly into the system, it's another thing. But when we run studies today, one of the parameters.
Μπορώ λίγο να παρέμβω. Είναι πολύ ωραία η συζήτηση η οποία γίνεται, αλλά είναι σε πολύ εξειδικευμένα θέματα της μοντελοποίησης και του προγραμματισμού και ίσως θα ήταν χρήσιμο να την κάνουν οι ενδιαφερόμενοι μεταξύ τους. Επειδή τώρα είναι παρόντες τουλάχιστον 30 ακόμα άτομα, θα ήθελα να ρωτήσω μήπως υπάρχουν και άλλες ερωτήσεις και μετά οι δύο ενδιαφερόμενοι μπορούν να συνεχίσουν όσο θέλουν την αλληλοενημέρωσή τους.
I have another question. Mr. George Miltiadou sent a question. He told me to read it. As the technology you investigated is considered long-term duration storage, have you benchmarked and compared these technologies with competing technologies such as latent heat thermal energy storage? In the presentation of VOIF, you illustrated values for load wind feed only for January to illustrate the gaps and the usefulness. Have you investigated spring-summer profiles?
To whom this question is addressed? Is there any specific person and presenter or somebody from the panel has to answer that?
No, anyone from the panel. He had this question because he have not seen yesterday's presentations.
Right. So, may I answer that, Antonia?
Yes, of course.
Yeah, thank you. This is Thanasis Katsanevakis. During the course of the project, merely all the available storage technologies have been assessed during the initial stages of the project, including the latent heat and all this stuff. During the run of the project, at the end of this project, some of them, specific of them have been selected for further investigation. Latent heat is a nice storage technology, but is directly related to the solar thermal power generation, and it does very good work there, but cannot be efficiently operate with PVs or with wind turbines and renewable technologies like that. So it has not been given more investigation in the rest of the project. That was actually the main reason for latent heat technologies.
Thank you very much, Mr. Katsanevakis. I don't know if Mr. Miltiadou is covered by this answer.
Actually, I think he was not in the lobby. Maybe he didn't hear the answer, but Can I add something on this?
Can I ask something to be more specific? Sorry, I couldn't hear previously. So when you're referring to that latent heat is not efficient with hybrid further to CSP such as PV and wind, can you be more specific on that?
Yes, of course, because the PVs and the wind generate actually electricity, and it is not efficient to change the electricity into heat and then try from heat to regenerate electricity. If you do the calculations, the thermodynamic calculations, you end up with a very, very low overall efficiency. This is the reason. Whereas the CSP, the concentrated solar power, generates, heat itself. So you do not have to change the nature of this energy into another energy medium and then rechange that into heat. So from solar thermal power, the concentrated solar thermal power, you can store immediately the heat you generate by the sun. That's why it's very much more efficient. And this is why latent heat is very much related to the concentrated solar power and does very good work there. Okay.
Yeah, totally agree. Thank you for the answer. But if I have excess from wind and PV, why I shall not use, let's say, multi-heaters or any type of elements to use air and then transfer it into latent heat? I'm not only referring to molten salt, but other technologies such as silicon-based alloys. And then having, for example, a Stirling engine to get the latent heat after or during night. Would you say 8 hours as the technology you presented?
It is very good, the idea, but it is not commercially, acknowledged. I mean, this is something very good to do a research project or something like that, but at the end of the day, this project had to focus to commercially available and proven technologies.
Okay, thank you.
Thank you very much, Mr. Katsanavakis. Does anyone else have another question for any of the speakers?
Just to clarify on the previous conversation that CSP technology is not commercial in a lot of countries. There are a lot of commercial plants in Spain and some other in I think in Portugal and now in Greece. It's a technology that it will be studied and it was accounted in the national NECP anyway. We have some projects in Cyprus that they have obtained license, but up to now we haven't seen in practice in Cyprus such a system. But of course, it's something that it will not be excluded from our planning on other studies or other models that we're gonna use. This is George from the ministry, just to clarify. Thank you.
Yes, George, we have taken into account this 50 megawatts CSP already in the models. Do you know that?
And CSP, it is a proven technology. Okay, CSP is a proven technology. Counts many years and decades of operation elsewhere, of course, not in Cyprus. Okay, and that's why also the latent heat technology of storage together with the CSP is a proven technology. Yes, it is. What I said before about the latent heat was for other ways of using the latent heat, as my colleague said before, which means alloys and things like that together with PVs or other renewables and so on. Okay, CSP is a proven technology.
Yeah, perfect. But okay, let's say back to the basics. CSP with the latent heat, as you agreed that is proven technology. Have you investigated the CSP with the hydropower or only wind and PVs?
Yes, I'll tell you that. CSP is a storage technology itself because it does have the capacity of storing for 4, 6, 8 hours energy to use that during the nighttime or anywhere. So the selection of technologies done during the initial stages of the project considered CSP. However, because of the cost of this technology, came to a result saying that if I have a specific renewable source, which is the solar irradiation, what is the best way to use this source? Is it CSP or is it PVs? Taking into account their efficiency in power generation, storage capabilities, cost of building the plants, and everything. The result of that early comparison was that it's preferable to use PVs because the price of the PVs is very, very low, and generate electricity and then try to store this electricity instead of using the solar irradiation, generate heat, and then turn the heat into electricity and store also a part of the heat for the needs of the grid. Okay, I'm just explaining the how the ideas were examined during the run of the project. Okay, so if you take into account the efficiencies of all these energy transfer changes between the various systems and the cost, which is finally related with each technology, finally the PVs combined with a electricity storage technology is more, more attractive. Say, not more efficient, not more attractive, because also reasons of the market and the cost and everything should be taken into account.
Perfect. Very much appreciated for the response.
Thank you very much, Mr. Katsanevagis. We have another general question from Mr. Polikarpos Polikarpou. We have seen the production limits in Cyprus and estimated how much more energy could be imported from Israel, Greece, or Egypt in case of interconnection of networks. Do you think that this limitation is a barrier of industry development in Cyprus that could be removed by importing electricity, or the extra energy imported is going to be wasted in increasing the energy consumption of the public?
I would appreciate George Partasidis, my colleague, to answer this.
Yeah, he had to go away for another meeting, so he said
all right.
And answer it in
so
writing.
Maybe Maria Eleni Dalenta from the regulator.
Maria Eleni, are you here?
So
we should answer this question in writing.
As nobody's willing to answer that, I would say that this is a matter of good housekeeping. It's not a matter of technology, right? Technology gives us the capabilities. Now, the way we are using those capabilities is up to us. It's a good housekeeping, nothing more.
So we'll come back to you, Mr. Polikarpou, with an answer by Mr. Partasidis, who is more relevant to answer the question. Okay, do you have any more questions from anyone? Okay, so this concludes the workshop. I hope you all found the information useful. Thank you very much for your participation and have a nice day.
Have a nice day, you too. Thank you all.